Functional connectivity derived from both signal correlation has been widely used to study interactions between human brain regions. Different factors can affect the correlation. One of them is the shared input from the rest of the network, labeled as V here. Another factor is the local coupling between the two neural regions, labeled as W. We try to answer two questions here. One, how can we decouple those two factors? And two, it has been found that the magnitude of functional connectivity during task is generally lower relative to resting state. With our proposed method to decouple the two factors, what can we say about the local coupling change from rest to task? Our solution is inspired by simulation. Increasing the shared input V changed both signal correlation and variance simultaneously, while increasing local coupling W has more effect on the correlation than on the variance. Therefore, if we remove the variance-related change from the overall correlation change, the remaining component will be particularly sensitive to local coupling and not so much to the shared input. So we call this remaining component communication change, as it indexes the change in the local coupling between the two neural regions. Empirically, there is an intrinsic positive relationship between the magnitude of functional connectivity and the temporal variance in the both signals. This is consistent with our simulation result. In fact, we can obtain robust positive regression coefficient using single-subject resting state data in all subnetworks. Using those regression coefficients, we can extract the communication change from correlation by removing the variance-related components. From resting states to task, communication change exhibit interesting spatial characteristics in real data. Check out poster to find out the detail.